Hello friends, welcome to my channel. This is Isro question paper heat transfer part 4. Question is, when K is the thermal conductivity, tau is the density, Cp is the specific heat of a substance, then thermal diffusivity is given by thermal diffusivity. We know alpha is K by rho Cp. Here rho is taken as tau. So K by tau Cp. Alpha is thermal diffusivity by it is the ratio of heat conducted and heat capacity or heat conducted by heat stored. It's K by rho Cp. Its unit is meter square per second. Whenever alpha increases, propagation of heat into the medium also increases. So from here our answer is K by tau Cp. A is the answer. The radiative heat transfer rate per unit area watt per meter square between two plane parallel gray surface, emissivity 0.9, maintained at 400 Kelvin and 300 Kelvin is Stefan Boltzmann constant sigma given. We have to find Q by A. Sigma T1 to the power 4 divided by minus T2 to the power 4 divided by epsilon 1 by minus 1. We will do part. This one already discussed. T1 is 400 Kelvin, 300 Kelvin. It's 400 square minus 300 square. A square minus B square. So A plus B into A minus B. 400 square plus 300 square is 500 square into again A square minus B square. 400 plus 300 into 400 minus 300. So it will come 500 square into 700 into 100. Here emissivity 1 and 2 both are 0.9. So minus 1 plus 1 by minus 1.81. So 1 minus it will come, it's 0.9. Here also 0.9. 2 minus 0.9 divided by 0.9. So it will come 1.1 by 0.9. So 11 by 9. Q by A is sigma T1 to the power 4 minus T2 to the power 4 divided by 5.67 into 10 to the power minus 8 into here 500 square into 500 square to 700 into 100 divided by 11 by 9. So it's 9 by 11. So here 2 to 4, 6, 8, 8 0, 8 0 cancel. So it's 5.67, nearly 2 times. So 5 into 5 into 7 into 9 by 2. It's 25 into, let it be 4 into 9. Take it as 8. 8 by 2, 4. So it should less than 900. From option we'll check. From option less than 900, C. So heat transfer rate for unit area. It's in watt per meter square. So no need to change. 8112 watt per meter square. C is the answer. Next, in a furnace made of bricks, inside heat transfer coefficient is 35 watt per meter square Kelvin. Outside heat transfer coefficient 25 watt per meter square Kelvin. Thermal conductivity of bricks 15 cm thickness equal to 0.15 watt per meter Kelvin. The overall heat transfer coefficient in watt per meter square Kelvin will be closer to, yes, we know overall heat transfer. U is overall heat transfer coefficient. It's 1 by H1 plus L1 by K1 plus 1 by H2. It's watt per meter square Kelvin. So area no need to be. So H1 1 by inside 35, it's 35 plus 15 cm, you convert it in meter, 0.15 K1 0.15 plus 1 by 25 will get, here it's around 0.02 plus 1 plus 0.04, so it will come 1.06. So U equal to 1 by 1.06. It will come 0. Convert it 100 by 106. So it will come watt per meter square Kelvin. So it's closer to inside heat transfer coefficient. It's 35, but we got 0.94, so A is not possible. Outside heat transfer coefficient, it's 25. 25 also not possible. Thermal conductivity of bricks, it's 0.15. 0.15, where we get 0.94. So it's also not possible. We go for D. Heat transfer coefficient based on thermal conductivity of bricks alone. U equal to K1. So U equal to 0.15 by 0.15, get 1. 1 is nearby 0.94. So D is our answer. Four rods with different radius R and length L are connected to two reservoirs at different temperature. Which one of them will conduct most heat? Fourier's law of heat conduction will apply here, one dimension. So here Q is proportional to L and area rod for area, it's pi by 4 d square, or it's in radius, so pi r square. Q is proportional to r square, and length Q is inversely proportional to delta L. So what we got? R square by L. So from all options we will check. Q, here R is from option A 2 cm by L is 2 cm. So if we square we will get 1. In case of B we will get R square by L square. This one we will use. Excuse me, R square by L. Here we will get 4 by 2, it's 2. Next R is 1 cm, L is 1. 1 square 1 by 1, we get 1. So C, R square is 4 divided by L. 1 by 2, so it will multiply. It's 8 T. R square 1 by 2 square is 1 by 4 into L is divided by 1 by 2. So 2 by 1. So it's 1 by 2. So in C, its Q is maximum 8. 8 is maximum. So C is the answer. If thermal conductivity of a material of wall varies as K0 into 1 minus alpha T, the temperature at the center of the wall will be, if alpha is positive, then how much? This one already discussed. Here in this case, T1, T2, both wall temperature. It's K0 into plus alpha T. Here K0 into 1 minus alpha T. Here K is constant. If alpha is positive at center, what will happen? K will increases. So alpha is positive, but our formula is already given in this question, 1 minus alpha T. So negative this one and get its center of wall will be less than in case of constant thermal conductivity. C is our answer. The spectral emissive power U1 for a diffusely emitting surface is U1 equal to 0 for alpha less than 3 micrometer, U1 150 watt per meter square micrometer. This one given, and total emissive power of the surface over the entire spectrum asked. So we'll draw that graph first. After that we'll go for the area, we'll get the answer. Three, then 12, 25. U1 equal to 0 for alpha is less than 3 micrometer. So after that it's 150, then it's 300. So here 150 up to 3 to 12. Then 12 to 25 it's 300. Then again after 25 it's 0. So this area we have to calculate for total emissive power. So total emissive power is or 12 minus 3 is 9 into 150 plus 25 minus 12 is 13 into 300. So it will come 1350 plus 3900. It will come 0, then 5250 watt per meter square. From option D is the answer. A wire is plastically deformed bent by supplying a force of 40 Newton over a distance 0.8 meter. The force moves in the direction in which the distance is measured. If the wire has a mass of 0.2 kg and a specific heat of 0.5 kilojoule per kg degree centigrade, estimate the maximum increase in the average temperature of the wire. Here our formula is PdT F into distance x. Put the values. F how much, M how much, mass of 0.2, then Cp 0.5, it's in kilojoule, converted joule, multiply 10 to the power 3. Change in temperature asked in this question. So it's then F into x. F is 40 into x 0.8. Then our change in temperature is 40 into 0.8, 0.2 into 0.5 into 10 to the power 3. It's 4. Then 0.5 we make it as 5 by 10. Then 5 to 2. 40 into 1000, it's 25. 8 by 25. So it will come around 0.3. It will come 0.32 degrees centigrade. From option A, B. B is the answer. Two rods, one of length L and the other length 2L, are made of the same material and have the same diameter. The two ends of the longer rod are maintained at 100 degrees Celsius. One end of the shorter rod is maintained at 100 degrees Celsius while the other end is insulated. Both the rods are exposed to the same environment at 40 degrees Celsius. The temperature at the insulated end of the shorter rod is maintained at 45 degree 55 degrees Celsius. The temperature at the midpoint of the longer rod will be its first one. Second one is insulated, that's shorter rod. So temperature at the midpoint of longer rod, both side 100 degrees Celsius. So mid also 100 degrees Celsius. D is the answer. A sphere, a cube and a disc, all the same material, quality and volume, are heated to 900 Kelvin and left in air. Which of these will have the lowest rate of cooling? From Newton's law of cooling, Q is H surface area into delta T. Delta T you can write as Q H AS into surface temperature, atmosphere temperature. So Q is proportional to AS. We'll check AS. AS for cube is 6A square and for disc is maximum. AS for disc is maximum and for sphere AS is 4 pi r square. In production for riser we are using lowest cooling rate, that is spherical shape is best. So D is not possible. C is our answer. Disc, in case of disc it's maximum cooling rate. So disc also not possible. A and C we can consider in that way. C is having lowest cooling rate in case of sphere. That's why riser design we are using spherical shape riser for ideal case. Thank you friends. Thank you for watching my video.